So, the last two lectures, whenever a course ends, people get happy. I used to get happy too. It seems as if some sort of brick is getting out of your head. But those who are just seeing the course just for seeing it, and even for preparing the exam for the exams, need not worry. It's not a brick in the head, but it's some sort of a, some sort of a strength that you acquire when you have learned the calculus. Don't worry too much about exams. Doing good in exams or bad in exams doesn't tell effectively anything about you. It's possibly one of the stupidest way to check whether somebody has learned something or not. There is a famous quotation by James Watson, one of the inventors of the structure of the DNA along with Watson and Crick, that except for mothers of scientists and some media personality, most scientists are outright dumb. So, do not worry if you think that you are not understanding things here, as I have not understood too much. And I wish that anybody who wants to take a career in science should read the book The Double Helix by James Watson, and you could see how much a human endeavor science is. It is not just sit down and it is done, things are done. Today I am going to talk about Taylor's theorem, but I might just be more freewheeling in this whole thing. Taylor's theorem is one of the culminations where you actually step in to do analysis. So, here once the Taylor theorem ends, actually advanced calculus also in my opinion ends. Then what you do is analysis after that. Wherever you use Taylor's theorem, its analysis and its applications. One of the key areas where it is used is, for example, optimization and which has huge applications. So, it is not just about just a result, but it is about how effective a result is. So, we publish a lot of papers. In science, you would observe that there is a huge amount of publication which takes place. There are too many scientific journals. I think they are outstripping the number of novels published in a year. So, the issue is that how much of that knowledge we really need. It is very difficult to say how much of that knowledge we really need, but the question is how much of the knowledge is effective. Nowadays, in this age where we are so much, deciding about what is important, what is practical, and to do science and think about it in its own practical ways, in the sense that do something which is immediately applicable to the needs of society. As it is important, but one has to remember that science and humanity has been most, though useful science is important, I completely agree, but one has to also admit that among the most important advancement of humankind is possibly done through useless science, rather useless science, or not, I cannot say useless, if that is useful I cannot say useless, but rather a science which is based on curiosity. So, somebody has some idea and he pursues it, whether it was Newton's thinking about gravity, whether it was the invention of the calculus, whether it was invention of many other things in mathematics, many of them, or even Einstein's theory of relativity, many of them are just curiosity. That you can use your GPS today is because of Einstein's theory of relativity. That rockets are being launched and our satellites are launched and put into satellite is a combination of special theory of relativity and Newton's mechanics, which depend on calculus. So, these were things nobody knew how effective it would be. When number theory was studied, nobody thought that it would be so important in coding, which is used in war and many other secret issues. So, every endeavor of humankind in science is actually effective, but it is ultimately it is this research out of curiosity which becomes truly effective, and this is what we have discussed all along in this possibly 38 lectures, is essentially a science which was developed partly out of curiosity, partly out of need, and partly out of some questions posed by someone. And the way of doing such science was has vanished. For example, many people wouldn't know, but I want to bring it. I didn't use this particular book, but I want to show this book to the viewers, and I wish that if anybody has any interest in mathematics or even engineering or whatever, you should really read this book, Introduction to Calculus and Analysis by Richard Courant and Fritz John. Richard Courant and Fritz John are one of the leading mathematicians of the 20th century. And there is a Courant Institute of Mathematical Sciences in New York in his name, and Fritz John is has a huge contribution in optimization. He made one contribution, and that is a huge contribution which changed the subject, and he has a huge contribution in the understanding of partial differential equation. And the interesting fact is that Fritz John actually worked in the Courant Institute of Mathematical Sciences. Courant is very famous for writing with Harold Robbins a book called What is Mathematics. So, when people do mathematics or people think about mathematics, most of us who are aspiring to be engineers or something, doctors or something else, are mostly people are aspiring to be engineers or doctors, which are in our country the most coveted of all professions possibly. People think that mathematics, what you done in class 12 and what is taught to you in the first year at your universities in engineering courses, that is what mathematics is. It is about some bizarre guys forming bizarre problems and you just have to solve it. No, mathematics is about ideas. If people had not thought about progressing mathematical ideas, you wouldn't have had the calculus. Because people are contented to do plus minus and doing daily course with mathematics. But people were more curious about how planets move. You might think that why should I bother about planets moving or not, I should just look out for my own daily life. The question is that you are really bothered about your own place in the world, in the universe, and you want to explain the world around you. And the need for doing so had actually made mathematics progress, and mathematics is progressing till that day. I want you to get out of this course with the idea that mathematics doesn't stop in your first year of engineering or in your first year of in a pass course. Mathematics doesn't stop there. That is exactly what I want to tell you. Students who get into mathematics would realize that soon, but those who wouldn't be getting into mathematics would go for other professions where mathematics is used. I want to tell them that is very important to keep in mind, that you should really go with the idea. You should never go with the idea that mathematics finishes with your first year courses. So that would be a big mistake and a big dishonor you would make to yourself, not only to mathematics. So now I will start with the idea which I had told I will tell you when I teach you sequences, but I forgot to tell you when I was teaching you sequences. So I remembered while coming here that I need to tell you. You remember that we had this important result that if I have a continuous function, if this is a function a b to r and f is continuous, then f is bounded. Then f is bounded. And the bound is attained. That is, there is f is bounded above and below, then there is a x such that f of x is the minimum value, there is a y such that f of y is the maximum value. And the bounds are attained. So you know this result. We have proved up to this part that it is bounded, but the bounds are attained is not true. was not proved, and I left it to discuss when I would talk about sequences. So what is bounded? So the range of f, which is the set of all fx x element of AB, this is bounded. This set is a bounded set. So this is a bounded set of real numbers, and this bounded set of real numbers has a upper bound and a lower bound, and hence it would have a supremum. So let us write supremum of fx equal to alpha. So what happens is the following. So now consider see how much mathematics is involved here in a very little thing. So consider this to be alpha. So now take any epsilon 1. Take epsilon 1 greater than 0. So take alpha minus epsilon 1. But alpha minus epsilon 1 is greater than 0. So alpha minus epsilon 1 cannot be the supremum. So there is an right. So there is a x1 such that fx1 is here. So there is a x1. So there is a x1 in this such that fx1 is here. Similarly, if you take alpha minus epsilon by 2, right, where epsilon by 2 is less than epsilon by 1, and you are decreasing epsilon, so you are moving towards alpha. So you have some x2 such that fx2 is strictly bigger than alpha minus epsilon by 2. This is the definition of supremum, that is all. So what you generate? You generate a sequence x1, x2, xn, and you see, as I make epsilon value smaller and smaller, I keep on having points fx1, fx2, fx3 near the value alpha. So I generate a sequence fx1, fx2, fxn, and this sequence fxn actually goes to in alpha as n goes to infinity. Now at a very important thing to note, what about these sets x1, x2, xn? So these x1, x2, xn all are lying between a and b. Okay. Now this is a bounded sequence. So bounded sequence has a convergent subsequence. So let that subsequence be xnk. So xnk is going to some x star. Now xnk for each k, because it is just a subsequence, xnk is also lying between b and also lying between a. Now in the limit as k goes to infinity, here obviously this is k going to infinity. So here we have applied the Bolzano-Weierstrass theorem. Just see how many what steps are involved. So here the Bolzano theorem, Weierstrass theorem is applied, that you have a bounded sequence, it has a convergent subsequence which goes to x star. So all of these convergent sequences are with that, all the xnks are also bounded between a and b because they are part of this sequence xn. So now as k goes to infinity, again what would happen? Is that a would be less than equal to x star and less than equal to b, which would immediately imply that x star is element of AB. So once you have done that, you have thought it out in this way. So what does it mean? That now I consider a sequence f of x and k, the subsequence, the functional value with the subsequences, that anyway goes to alpha because the whole sequence is going to alpha. that anyway will go to f. Once a function, once a sequence goes to a limit, whatever subsequence will take you take will go to the same limit, because lim sup would be finally equal to lim inf, which I have spoken in the last class. So now as k tends to infinity, what do we have? Because f is a continuous function and x n k goes to x star, we have showed that in that case f x n k goes to f x n k goes to f x star. So you have limit of f x n k, k going to infinity equal to alpha, and this limit is nothing but f x star. So f x star is equal to alpha. So there is a x star in AB for which f x star is alpha, which is the nothing but the supremum of the function values. So here is a proof. So you see how many ideas are required to actually finally come and prove this fact. So this is one way of doing it, there are many other ways of doing it, but this is the most elegant way of doing it. So we will start talking about Taylor's theorem. Now Taylor was actually a student of Newton. Newton actually had started talking about calculus, but most of his proofs in his famous book Principia Mathematica, the mathematical principles of natural philosophy, it is possibly one of the greatest scientific books still, not only by its rigor but also by the level of the way things are done, and he had used tremendous amount of geometry there. Now Subramaniam Chandrasekhar, one of the most famous astrophysicists of our times, Nobel laureate, is a Indian American, but when he was an American citizen when he got his Nobel Prize, and he in 1983, he in the last 10 years of his life decided to do something which is unique. He decided to read the Principia, Newton's writing, and he wanted to take Newton's theorems. In fact, people wouldn't know that Newton has written his Principia in terms of proposition, theorems and lemmas and all those things. Not theorems, they didn't call theorems at that time, propositions. Proposition means I propose this, because ultimately they dealt all with natural phenomena, so people can change assumptions and things can change. So what happened was that he said, I decided not to look into the solutions, but use the solution, do the solution using modern techniques. So in most cases he found that when he had actually covered a result, when he proved a result by working through 2-3 pages, he found that Newton had already solved it. When he went back to Newton's solution, it was done in half a page, because Newton used to use geometry. So this word Newton for calculus, so at that time they were only talking about mechanics. So everything was taken, every function was a function of time, right. So Newton used to use these symbols, x dot t. So x dot t, x double dot t, all these things. While Leibniz, his so called rival in Germany, would use these signs, y, y dash, y double dash, y triple dash and so on. So these are this is Newton's, this is Newton and this is Leibniz. So there was a great rivalry as to who had first got to the calculus. Calculus is all about change, actually. Calculus is about how you study change, but everything in nature is changing. So see, there is a lot of, so this is very important to understand, lot of mathematics has come trying to understand nature, natural science. So that is trying to explain the world around us. Those who are more scientifically curious here should read a very nice book written by a Nobel laureate physicist called To Explain the World. There he starts from Greek science and how it went and comes up to Newton, and you would see how the ideas have evolved. So scientific ideas take too much time to evolve. Now this idea of Taylor's theorem which you might have seen in books. People write like this. If you open a calculus book and go to the Taylor's theorem chapter, you would see something written like this. Derivative f dash n x minus a plus. So, if you know the function value at a, you can calculate the function value at f x. Something, and it just possibly goes on like this or ends somewhere with some term. So, which term I will call say R n, say ended at the n after the n derivative. So, something you will look at something like this. Now, you might be wondering as to what is all this, what does it mean? So, if you know the function value at a, you are saying that I can calculate for any other x, I can calculate the function value of x. Why take so much trouble? When I was undergrad student, I was worried about unable to explain myself why should I do this. So, one day I realized, I just figured out, I thought that okay, suppose somebody gives me to calculate the function sine 41 degrees, how would I calculate it? I know sine 30 degree, I know sine 45 degree, but I do not know what is sine 41 degree. Then I realized that the interesting part of the Taylor's theorem is that for these sort of functions where calculating function values are not always easy for every x, you convert that calculation, for example, with for trigonometric function or transcendental functions like e to the power x and all, or logarithmic functions, you convert the calculating a function value at a given point. Once a particular simple reference point the function value is known, you can convert the calculating the function value at any point into simple basic arithmetic operations: multiplication, division, addition, subtraction. 4 basic operations. But these ideas did not just come from the air, they all came from a single theorem which you have all studied at high school, is the binomial theorem. And that was what Newton was teaching to his student when Taylor caught on to the idea, and Taylor first thought it out for polynomials. When Newton was interested in polynomials. So, why they were interested in polynomials? They were interested in polynomials because at this time they will have a lot of astronomical data. So, you will have t values and then you will have x values and you will have y values, but you do not have a function. So, you will make, looking at the natural phenomena, you will make some assumption about the relation between y and x is a continuous type of nice looking thing, and then you will try to fit a polynomial into it, which is called interpolation or Newton's interpolation. You will start learning when you start learning or engineering or whatever you want to study. So, Newton was also talking about emphasis on these interpolation techniques, how to really figure out the shape of a function or estimate it roughly. As I told you, the Bertrand Russell often said that exact sciences are more to do with approximations. So, then he caught out, Taylor, that you can actually use this to calculate exactly the function value of a polynomial, and then one went to other things. So, then Newton caught it that okay, and Newton told him that you can actually also go to the other cases by this method. Many times maybe an important result like Taylor's polynomial is beyond the threshold of publicity for a person like Newton. For publications he did not bother. He simply told Taylor that you can just okay fine, it is good for this polynomial, it is done, but you can actually do it for non-polynomials also, and this is the way to do it, which is now known as Taylor's theorem. For example, many of you who use the L'Hospital's rule or L'Hopital's rule if you speak French, the result was known actually due to Bernoulli. John Bernoulli. It was not due to L Hospital. L Hospital, he was a tutor to L Hospital. L Hospital wrote a book on calculus in which he wrote about that technique. But he became to be known as L Hospital's rule. Now we will talk about this the story of Taylor's expansion from the book of Courant and John. Why I talk about Courant and John and why I tell you to read it from here. I am not marketing Courant and John, right? Both Courant and John are not alive. The idea is that they are so historically rich and you know why such things were developed. There are always reasons why things are developed, because just after this he talks about numerical solutions of equations, he talks about interpolation just after Taylor's theorem, because that is exactly the reason why all these things were developed. Because this is something you know in your school, high school, and I was also taught when I was in high school. In Calcutta there was a small book called Dash and Mukherjee's calculus, and we used to take a great pride in able to solve the integrals there. So, this is if I am not wrong, I have my TS sitting here, so I can just, it is always good to speak to people when you lecture, they can correct me if I am wrong. So, x a 4, x a cube or something, I do not know, I just have to check. This just goes on basically. So, like this is called it is an infinite series, but it is not fixed numbers like a1, a2, a2, it is with x's. So, for every x it need not converge, it only converge for x strictly lying between +1 and -1, that is mod x strictly less than 1. This was already known to Newton, and you similarly had this for 1 plus x, which was 1 minus x plus x square minus x cube. And the x 1 means x to the power 0 basically, and so on. This is also true for mod x. So, if n is odd, it is -1, +1, then -1, then n is sorry, n is n is x. I am making a mistake, something like that. I have forgotten. But basically, when n is odd, you will have minus. When n is even, you will have plus. So, you can -1 to the power n, right? Because when n is even, you will have +1, when n is odd is +1. So, this is similarly you can write for 1 plus x square also, 1 by 1 plus x square. Now, you might ask me why, what is the big deal, I can calculate it. But if I give a very bad x and 1 plus x is a very bad number, then 1 by 1 plus x, that division is not easy to carry out very fast. If I give x is say 20 lakhs, carry out that 1 by 1 plus 20 lakhs plus 1. It is very difficult to, I give you 3 minutes time, 2 minutes time, approximate it. But you can immediately plug this in, 2-3 values, and immediately give a rough approximation. So, you see that you will be able to immediately do a lot of approximations if you know that I can express functions in this sort of way. So, what is this value 1? It is the value at x equal to 0. So, it is the same x minus a here only x minus 0. Since similarly in, so this is what is essentially the generalized A rule, the binomial rule, which says that if you have 1 plus x to the power alpha, then you have 1 plus alpha x plus, I just have to, I do not remember the combination alpha, when alpha by 1 factorial, then alpha into alpha minus 1 by 1 alpha C2 basically, but we cannot write alpha C2 because they need not be integers, positive integers, x square and so on. So, this is the general rule, it is a general binomial theorem. So, these are all, so this general binomial theorem is not ending, it is just going on, it is a infinite series. When you have positive terms 1 plus x to the power some square, then it ends and it becomes a polynomial. So, now what we will learn that many good examples of this, but let us just see what is the meaning of this and then we will see what Taylor had done. So, in this first class let us just take what is the meaning of all this and then go to what Taylor had done and write down some important results. See, how do you actually sum and how do you know what is the meaning of this, right? So, basically we are interested now in power series. This is called a power series which looks like this, what you have just wrote for 1 by 1 minus x and 1 plus 1 x to the power minus 1 and 1 minus x to the power minus 1, but they look like this, but just we are putting in some more coordinates. So, how do you sum such a series? Again you sum it through just your standard way of taking partial sums. So, suppose I write okay, partial sum is this. So, if I write down the nth partial sum as this, what do I mean? These are n plus 1 objects, so components, but what now? Suppose I write down this formula fx and I say fx is equal to summation nu is equal to 0 to infinity a nu x to the power nu when mod x is strictly less than sum a. Here it was strictly less than 1. So, what does this mean? So, in this class we will try to understand first what does this mean and then you see how effective the understanding of Taylor's theorem would be for you. Okay. Now, this is my nth partial sum and this is my limit when x is this. So, what it means that fx is not equal to Sn. So, fx mine is equal to Sn plus some additional term which I call the remainder term. Remainder term. So, what is remainder? The remainder term is actually nothing but the error term. It is the error. It tells you how much you are left, what is the gap between fx and Sn. Now, so this term is called the remainder after the at the level of the nth partial term. It is called the nth remainder after the nth term. So, similarly if I take this one, so I can write this as 1 by 1 minus x as 1 plus x to the power n plus Rn. So, this is my Sn. So, if you calculate Rn now, just taking this part and subtracting and doing the simple fraction thing, then in this case, this particular case Rn would become x n plus 1 by 1 minus x. So, when mod of x So, what I want to do? So, when mod of x is less than 1, so if I now take mod of Rn, so when mod of x is less than 1, I am bringing it here. So, mod of Rn is equal to mod of x n plus 1 by mod of 1 minus x, okay. When mod x, whatever, mod of Rn, this one, I am just bringing this one here. So, now what is the idea behind this? The idea is the following, idea is that if n becomes larger and larger and larger, as n becomes larger and larger, I am having a better and better approximation of fx by Sn, that is this term should go to 0 as n goes towards infinity, that is the meaning of the remainder term, the error term, error must vanish at infinity, right, that is the clear idea. So, when will this go to infinity? When mod x is less than equal to 1. So, when if mod x is strictly less than 1, then limit of mod Rn n tends to infinity goes to 0. Because basically I do not know whether it is positive or negative, because I want this distance should be made as small as possible, that is all. So, which means that this fx can, which means that this is meaningful, at least this is meaningful or that is meaningful when mod x is less than 1. So, this is the key idea behind the fact that I can always use a power series to approximate a function. So, that is the idea behind Taylor's theorem, use a power series to approximate the function. But for the Taylor's theorem, this ANUs has a particular form involving these derivatives. These are your ANUs sort of thing, and that is what we are going to discuss right in the next class, which is essentially the last class of the whole syllabus. So, we will come back in few minutes and discuss, rather this is actually 2 classes I am taking in continuation, because that, so this class and the next class one after another, but we will just stop here and then we will discuss after some time, which I should now mark as Taylor's theorem, other issues, and end of the course 2. Other issues, of course, you might ask what is the other issue. One issue is that sequence issue I just told you, and the other issues are the stories that I am weaving inside the narrative, and that is also important, some stories has to be told. Okay, thank you very much.